Okay, students, let's begin lecture. It's 3:30. Um, in case you're wondering why things look a little different, my MacBook is in the shop for repair, and so I had to borrow this Dell laptop, which is a Windows computer, and I have to use PowerPoint, and so I haven't got everything the way I like it, but we'll persevere. Our main topic for today is work, the physics concept of work. We're going to do some clicking. Have your clickers ready. But before we do that, we're going to turn in written homework 6 about boxcars. And folks coming in late are going to squeeze in. All right, now, the people that I want you to bring up yours directly to the front desk. Last name's LMNN. LMN. $50-50 chance. Last name's LMN. All right, great. Wait a minute, is your name on there? Okay, yeah, okay. Good. All right. Good. Okay, good, thank you. Wow, I don't see any pictures. I don't see any diagrams.
Do you want a diagram?
Oh man, I don't see much of all.
Wait,
it didn't say diagram.
It's good. No, it didn't.
Can you read my name?
That's got a diagram.
Can you read my name?
Chelsea
You already
Minor.
drew the diagram. Sebastian.
Oh, nice diagrams.
Oh, okay.
No,
Are you gonna take
didn't
off
have to.
your
No,
weights?
you didn't
I
have
wrote
to.
my explanation.
No, that's good.
Better
It's a
work.
communicate. Oh man, there's a sketch over here. Nice. A caboose.
I have a question. Basically, to solve this, all you have to do is what you said in class about the astronaut, like F astronaut spacecraft equals negative F spacecraft on astronaut. So if I want the astronaut to solve for negative F spacecraft.
Something like that. Yeah.
Okay, because everybody got a different answer.
Yeah.
And the one time that like I wasn't sure about it, you're my grade. So.
Okay, good. We'll see how it goes. LMN. Get your homework down here. And this time, no fooling around. Okay.
No funny business.
All right, good. LMN. LMN. Nice. Thank you. LMN. Bring it up now, forever hold your peace. Okay, the rest of you, send it to the aisle and then downhill. Homework, lovely homework. Come on, hurry up. Get those papers down here. Thanks. No, 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 that's cheating. Take that back. If you're not coming to class, give me your clicker back. What is your name? Dude, what is... I'll find out. And you're in trouble too with the hat. That's cheating. And anybody else that does it, if I don't see it, that doesn't mean... Oh, now All right, let's see the rest of this homework. You got it? Yeah, he took off. He didn't even want to tell me his name because he knows. You got somebody else's too, right? You got more than one. Yeah? Because I saw you doing something with some other guy just before that. Oh, the guy in the back row by the railing with the baseball hat on backwards. There's no more perfect way to get my attention in a very bad way than what you just did. Very artless and ham-fisted. All right. All right, let's get going. We're going to... You know why we don't do clicking on exams? Because the students in this class over the summer were cheating on it. And we nailed a bunch of them. All right. We're dipping backwards into chapter 7. This is a small blurb out of chapter 7. And let me repeat, forgive me for not having the normal format of slides and stuff that I usually do. I'm kind of at wit's end with Windows. The concept of work has a fairly precise definition. You know, if you're sitting in the cafeteria, the food court over at the student union, oh yeah, I got to go to work. It means you got a job. And that's a good definition. You have a job. But in physics, what it means, it has to do with changing the dynamical state of an object, specifically causing a small displacement in a particular direction. All right? Now, when I say displacement, I mean a small, maybe a very, very small line segment. If you're on a curved path like this, go ahead and draw a curved, kind of generic looking path, with a top to it, like something like a hill. Doesn't have to be any particular shape. And I'm calling this one path sigma, just to give it a fancy Greek name. All right? segments of that, you can think of that curve as being a set of line segments. Matter of fact, that's how the computer draws it. You use the cursor to shape it, and what you're really doing is choosing pixels on the screen to be connected by a small line segment. So small that it looks smooth. But if you were an electron, this would be anything but smooth. But for us, it looks smooth. And so a force that causes an object to be displaced means you're at least in motion. And in fact, work implies that you're changing the speed. And I'll give you the definition of it in a second. Oh, let's see if I can get this thing working here. Come on, baby. Oh, I guess I got to go over here. Okay, so on a generic path sigma, a small increment delta s. Now notice that I'm not using delta x, delta y, or delta z. That's for rectangular coordinates. You may have a free fall, along the z-axis. That's perfectly fine. This was kind of curved, and if you're on this path, you can use the generic symbol s to represent position along that path. Right? So a small increment delta s has its own geometry, and you can see that. I mean, it's some of them are slanted up to the right. Some of them are slanted down to the right. A few of them up here near the top, they're kind of, where's my cursor? Oh man, this cursor is too tiny. Well, anyway, so you got different slants, So if you say, all right, I'm going to make each pixel for my first approximation 1 millimeter. Then each 1 millimeter, if I'm going to make each increment 1 millimeter, then each 1 millimeter increment, each 1 millimeter line segment is going to have a different tilt, slightly, unless you're on a straightaway. But I think everything here has actually got a little bit of curve to it, if you look at it carefully. Although it does look kind of like a straightaway down here in the lower right. Now that is independent of any forces that may be acting. All right? So if I have some kind of a mysterious rightward pull force, you're hauling on this object, it's moving along this path, and you're getting, 22 newtons to the right, a constant 22 newtons to the right, horizontally, or you might be getting, a constant downward weight force, 96 newtons downward, or whatever it happens to be. Now that's independent. So the path and the force, they have their own geometries, and they have to be reconciled. You have to study them carefully using trig. So what we're going to do is study this generic path, and we're going to say, all right, let's subject objects on this path to a rightward pull force, 20 newtons to the right. Right? So that's what this black arrow is. All right, and then what I want to do is go ahead and choose out a couple dots on there. And each dot, each location, gives you the location of a different delta S segment. And delta S is tilting up to the right for this first dot, right over here. And then up here, delta S is way up at the top of the hill. And then down here, we got another one on the downhill side. Now, that's assuming you're going from left to right. All right, if you're going from right to left, there's going to be an awful lot of slowdown on this thing. I mean, you're going to get, if you're moving from left to right, you're going to speed up a little bit for every increment. Now, some increments you won't get much speed up. Now, here's an example. We've kind of implicitly been working with this idea of F parallel, the force parallel to the segment, and when we talked about ramps. Because it was, remember we broke down the weight force into the component of the weight force perpendicular to the ramp, and then a component parallel to the ramp? And it's the one that was parallel to the ramp that caused it to speed up or slow down. Okay, and that's kind of what we're working with here. So this formula here F parallel means the component of the force that is parallel to the increment delta S at any point where you compute delta S. So F parallel down here at this first dot is going to be different from F parallel up here at the top of the hill and F parallel down here. Because the segment is different. You know, the delta S segment has got a different tilt. Question? Yeah, is it related to the tangent line? Actually, F parallel is tangent, you know, the component of the force that's tangent to the curve. So correct. All right, and then F perpendicular, you know, you don't need it for work for various reasons, but that would be, you know, perpendicular to the tangent. So you would draw on a tangent line at any point, and that's what that's what you do for making a curve. You have a bunch of different line segments, and they're tilted at a different rise over run, and you chain them all together gracefully. It looks like a nice smooth curve if they're small enough. Okay. Another question. By the way, I'm recording this, and I know how to render this into a MPEG movie, so I hope I can upload it into YouTube this afternoon. But it's a little shaky on this Windows. It's so easy on the Mac, but it's kind of shaky on this Windows computer. But I'll try. I think I know what to do. Now, it says F parallel times delta F. So that's actually the work. The force parallel to the displacement times whatever the displacement is. Now that's a Newton times a meter. You know, and it might be a very small fraction of a meter, but I mean you know, the units are newtons and times meters. Okay, now that's equal to work. So the unit of work is a Newton meter. And you can make a note to yourself, a Newton meter. Let's see, a Newton is kilogram meter per second squared. All right? And so kilogram meter per second squared times a meter is kilogram meter squared per second squared. And so go ahead and write that down. A Newton meter is the same as kilogram meter squared per second squared. And in the metric system, that has a fancy, dancy name. It's called the joule. Joule, after the British scientist James Prescott Joule, who figured out a whole lot of energy concepts, specifically, most importantly, in the area of thermodynamics. So they named the energy unit, the work unit, after him. Now, what is delta KE? Delta KE is the change, delta, in something called the kinetic energy. All right, now, kinetic energy, here's the definition. It's a scalar quantity. It's not a vector. And we call it the energy of motion, kinetic energy. That means motion energy. And it's just 1/2 times m times v squared. Now, you can see momentum in there, but it's not exactly the same. Anytime you have the square of a vector, you're implicitly taking out all the directionality, because you're taking a product of two vectors, and when that happens, you usually have a scalar. So this is there's no directionality to kinetic energy. So you don't say, well, my kinetic energy is 5 joules to the west. No, you can't say that. You could say, well, I have 2 kilogram meter per second of momentum to the west, but you can't say you have any number of joules to the west, east, north, or south. You just got joules. All right, so it's a quantity that encodes the speed but not the direction. And it's mysterious. And in that, in Einstein's theory of relativity, the kinetic energy, any energy quantity, corresponds to, or is it corresponds to the direction of time. Momentum components correspond to the direction of motion, the velocity. Come on down to the front. Go ahead and make yourself at home. I don't mind. Just don't break your neck. Stepping over the... Yeah, so momentum has some direction to it. And you could say, well, the directionality of... But there is no direction to time. Time is time. It's the fourth dimension, and that makes energy kind of mysterious. And we'll put them all together into a four-dimensional dynamic vector here in probably next week sometime, before spring break. All right, let's do some iClicker questions. So break out your iClicker, if you will. And I'm just going to give you some kind of generic concepts. Yo, with the baseball hat up there in the back row, come down and see me before you leave. Yeah, definitely. All right, clicker question. Work in geometry. All right, A, B, C, or D. Think about it. Where does this horizontal pull force line up perfectly parallel to a delta S line segment? And let me start the question. Go ahead and turn on your clickers and start it. Okay. Okay, hit the refresh button if you haven't already. Got it. Good. Let me see what you guys got here. I'm so used to using a trackpad. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, most of you got that one right. Here's the answer. B. Yeah, and so go ahead and add that to your sketch. And why is that? Because at the top of the hill, you're basically level for just a second. You know, for just a few centimeters. You know, if you're on your bike, if you're on your bike up the hill, your bike's tilted like this. Okay, but at the top of the hill, your bike is perfectly level, at least for a second or so, and then you're going back down the hill. All right. Now, if you have a horizontal pull force, let me ask you, how many newtons will be in F parallel at the top relative to point A? More or less? More at A or less at A? Less at A, right? Because it's parallel, right? Or should it? Don't at point A, it's not parallel, right? So B, it is parallel. So which one has more newtons of F parallel? B, yeah, definitely B. Yeah. Matter of fact, if point B really is perfectly at the top, then all of that horizontal pull force is F parallel. Now down there at point A, you might have 37 out of 40, or some fraction of the full one. But up there at B, yep, you got it all. Now, next question. This one I want you to think about carefully. Why doesn't the force perpendicular to the path change the kinetic energy? Why only F parallel? In other words, why not F perpendicular? The entire room is gone quiet. Yes! I've got you thinking. Good. Dr. B strikes again. Oh my goodness. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop. Let's see if I can move this thing out here. Oh, I gotta use this thing over here. Oops, gotta go the wrong way. This is kind of primitive using this computer. Okay. Now, a whole lot of you guys chose A. So let me ask you this. I caught all those people with A. What is that? The majority of class napping. How can F parallel be canceled out by F perpendicular? Right? So the normal force cannot cancel F parallel. Right? So that one automatically you have to avoid. Let's take a look at B. Centripetal forces do not change an object's speed. Is that, now, why is that? That is true, but is that the correct answer? Why is it true? Why is it that a why? Did you answer that? Yeah. And so wild, crazy guess, but good instinct. But how would you explain it? Centripetal force isn't actually, it doesn't exist? Incorrect! I have to go to the other side of the room, over here. I'm going over here. Who's got centripetal? Go ahead. Shh. I gotta hear this. Come on. Incorrect. We're talking about centripetal forces in general. Up here. Go ahead. Incorrect. But you're not thinking in general terms. In general terms, a centripetal force doesn't add to the speed for what reason?
Does that have to do with the fact that speed's a scalar?
No, it doesn't have to do with the fact that speed is a scalar. Go ahead.
Is it because like a force pointing towards like the center of Earth is always going to be like 9.8?
Not 9 point. Nope. You're thinking 9.8 free fall. Gravitational interaction. No, you already had a chance. You can't. You thought. But do you want to try it again?
Well, what I was going to say is that the centripetal force was guided by the normal force, so it wouldn't really interact directly with speed.
You're getting warm. You've redeemed your honor. So, no, no, not Rachel. You, yeah, you had your hand up first. Shh, shh, shh. That's right. Centripetal force doesn't, affect the speed. But why is that? Okay, Rachel, you go ahead and follow up. Not general enough. There's something general about centripetal force that, with the baseball hat, the light blue baseball hat there in the middle. Yeah, you. What is your first name? Daniel. You flailed on the first one. You whiffed. But now you're on base. You got a single. Okay. Okay. There's something about not interacting. All right. Go ahead.
I was thinking since force is F equals ma, acceleration is the slope of velocity. And you can in turn say that the slope of the speed is the acceleration. So if you have a perpendicular slope, maybe there's...
You're mixing, yeah, you're talking about the acceleration as the slope of a velocity graph, but that's different from the physical tilt of a centripetal force vector compared to the path. What is your name again? No, not that guy, you.
Me?
Yeah. Daniel. All right, we're going across the way here again. See, okay, you're thinking, Samuel.
So is it because we're talking about kinetic energy in a horizontal motion, not perpendicular?
Could be any centripetal force. What does centripetal mean? Toward the center.
The acceleration is always going towards the center of the circle, so it doesn't really speed up, and it's
You're burning up. Just stand up and say that again, so everybody and face the. Yes, I do. See if you can repeat what he's. Because it's good.
Basically, you're accelerating towards the center of the circle, so you aren't really speeding up. Like the centripetal force, you're always accelerating towards the center, and it's angular velocity, not really.
Yeah, the center of what?
Of the
Center of the circle, right?
circle.
But what if you're on a generic path like the one we have? We don't have. That's not a circular path. You have a radius of curvature at any given point. So the acceleration is toward the radius of curvature. Now, what's the property of that circle? It's called the osculating circle, the radius of curvature circle. What's true about that relative to the path? How are they related? It meets it at one point, and for that one small neighborhood, what's true about the two figures, the two geometric figures? They're the same. They're the same direction. What's the relationship between the velocity and that circle? The velocity vector and that circle, either the curvature circle on a generic path, or what do you got there? Yeah. Velocity is tangent to the circle of curvature. And what about the acceleration? There you go. The acceleration is perpendicular to the velocity. So you don't get any speed up and you don't get any slowdown. And for that reason, let me move this back over here. There's your correct answer. Centripetal forces do not change an object's speed, only its direction. Now, force that changes its speed, you've got to have a few newtons, either tangent to the circle of curvature or the path, or the opposite direction. That'll slow it down. Right? But if you don't have that, if you have something perpendicular, you don't get jack. Not on the speedometer. All right? And that's what kinetic energy is about. All right? So that's why we focus on F parallel. If we care about the speed, v squared, then we know ahead of time that F parallel is all we need to worry about. Now, there's some trig in all of that. And we're going to do some more work on that. Your homework, I'm going to dismiss now. It's a good place to break. Your homework is you can now read chapter 8.4 in the momentum chapter, because it talks about kinetic energy, and you got enough that you can be conversant with that. So I'll see you on Monday, and hopefully by Monday we'll have a lot of things caught up in terms of grades and stuff.